So I guess we can start the workshop. That I'd like to welcome Erik Michiels from IBM Quantum. He gave the first workshop in the first semester, and from your feedback, we heard that it was a bit too, let's say, theoretical, not very hands-on. So with today's workshop, we hope to give you an actual hands-on experience to tackle some actual applications of quantum computing. And I hope that you will have a wonderful experience and just enjoy the day.
Thank you, Jago, for the introduction, and welcome on this workshop, I would call it, around quantum computing with Qiskit. Before really doing the hands-on exercise, I would like to give also a kind of short introduction to quantum computing. You might already have heard several things about quantum computing, already got courses about it. That's not a problem. I will not do a complete overview, just I will repeat some essential elements. It might be for some people a kind of confirmation of what you already have learned. A confirmation is always also very good, I think. For some people, there might be some new elements. Of course, we will do a lot of practical hands-on. I have here a small plan, and I also will present that in a couple of minutes. I will do it now. You will see that we have a lot of practical things in the course. Yeah, that's it. So that was the plan. Of course, a plan is always subject to change. I did not indicate timing because we need to be a little bit flexible. That is the ambition. The ambition, perhaps some things might be skipped because we don't have enough time, whatever, but that is the ambition. So first of all, a kind of introduction, also with some mathematical concepts that are behind quantum computing. Basic, but interesting to know. Secondly, I will show you the IBM quantum computing systems that we are going to use today. You can access them for free. Jago and the team already asked you to create an account to access these systems. That should work. That otherwise you lose a bit too much time. It doesn't take so much time, but yeah, we continue with the exercises in the meantime. So yeah, I will do then a kind of demo and then give you also the possibility to make your first quantum circuits. And I will repeat what a quantum circuit really means. Then we will go over to Qiskit, Quantum Information Systems Kit, the open source development kit for quantum computing. And there we will make a first easy exercise. As in all programming languages, you know, there is something like hello world, but we also call this hello world, although we will not display hello world. We will see, we will create the belt state with our Python program, because Qiskit is based on Python. Okay, then, by the way, and before we will not install Qiskit locally. But I tell you the reason. Recently, we have had a new version of Qiskit 1.0. This new version, it contains quite some changes with the previous version, Qiskit 0.49. We could reinstall Qiskit 1.0 again, but that could take a little bit too much time. So we are going to make these exercises in the cloud, Quantum Lab, and that works also very fine. So, okay. Then, we will also make an exercise, I called it the quantum adder. So how can you add values in quantum computing? A break, of course, we can be flexible. Then, a small overview of popular quantum algorithms, a little bit of complexity theory behind it, without going too much into detail. I am not, of course, a professor. I am working for a commercial company, and everything we do in mathematics and physics is a little bit explained in a more democratic, easier to understand way. So, let's say then we go to an exercise, quantum teleportation. It's an algorithm to quantum computing without proof. Just we will make it, and then I would like to go to the Bernstein-Vazirani algorithm. That is the ambition. With also a small proof, or to make you understand why that algorithm is doing what it really is doing. And also on suggestion of the organizing team, I would like to tell you a little bit more about quantum machine learning and even give you a small kind of demonstration what that is really about. Okay, so it might be that some topic is not tackled, but I can provide you with Jupyter notebooks if you would like to do it afterwards. Yeah? If there are questions, don't hesitate to interrupt me. Next, we are going now to a small introduction on quantum computing, kind of repetition for some people, as I said. And I will do a check immediately if it is still interesting after explaining this. First of all, quantum computing is not going to replace our classical computing, but going to be a complement to it. That's the goal. You see that here? The set of problems that we are going to solve with classical computers in the white Venn diagram. It's represented as such. And then you see the light blue, the set of problems that we are going to solve with quantum computers. First of all, the white Venn diagram will not be replaced. It will stay important. It will still be, it will be used daily. And we do fantastic things with these classical computers. Let's think about generative AI and this new wave. Think also about Internet of Things and all possible. Our world of today, we cannot imagine anymore without IT, you could say. IT is our life is full of IT. So that is fantastic and that will not disappear. But what we see, some problems are really difficult to solve or even impossible to solve, or not, the result is not accurate enough. And there we see that quantum computing can complement quantum computing. And I give you a very small example in the sector of the banking world. If we talk about transferring money from one account to another, there a classical computer is still the best solution. But if we talk about determining option prices, the prices of complex financial products, there banks think about alternative approaches like quantum algorithms, like quantum amplitude estimation, and alternatives to Monte Carlo simulations. So that's a complex things. There we start working in the light blue. Yeah? And of course, there is still the red zone. Really a zone where quantum computing, we don't think it will be able to help us. There are still problems that are anti-hard problems, as we call them in the complexity theory, that will probably even not be solvable with quantum computers. Yeah. Okay, so it will be clear for everybody. Am I still on the same page as you? Is it interesting like that? Yeah. Because don't hesitate to ask questions. Then I'll come now to a very important slide. That is making the difference between our classical computing and quantum computing from an IT supplier point of view. The left-hand side, you all know. It's about bits. Bit can be 0, 1. And the Boolean logic, Boolean gates, you all know it. We are not aware about it anymore, but everything we do, you are scrolling, the lady is scrolling on her laptop that is based on underlying bits. You're looking to your smartwatch that's based on bits with Boolean logic. So everything is based on that concept. In quantum computing, we have a completely different type of approach. We have, first of all, qubits, and a qubit has a big difference with a bit, as you might know. At a given moment in time, a qubit can have a status 0, a status 1. We call it a linear combination of both. We call it a superposition state. You have an excited state, you have a ground state, and you could represent that as a point on a sphere, the Borg sphere, with a radius 1. You might did you already see that in some courses, that aspect of qubits? Yeah, you already saw that. Okay, I will not lose too much time with that anymore. Okay, and then you have a way to make use of the qubits. You are going to manipulate them with quantum gates, and these quantum gates are going to operate on the qubits. And the goal is to combine these gates in a smart way so that you do a meaningful representation of the problem and a meaningful solution of the problem as well. And at the end, you are going to measure, and then the qubits are going to collapse in classical bits. That's the goal. Yes. Is this something you all know about already? Known material? Yeah. Okay. I will not repeat too much. Then a couple of things. We call the number of qubits. We call that the circuit width, breedte, and the circuit depth is the number of layers. And the goal, of course, is to increase the number of qubits, to increase the number of layers, so that you can do more powerful computations. The big challenge in this increasing the width, increasing the depth, is the noise. We still don't have perfectly working quantum computers. Even there are different types of implementations. Within IBM, the implementation is superconducting transmons based on superconducting phenomena. It's not the only technology that exists. There are other technologies based on ions. I recently saw a breakthrough also in the usage of neutral atoms. There are even more alternatives. As a company, IBM is following up all these evolutions. But at this moment in time, we invest a lot in superconducting transmons. So that is our main domain of investment, and we want to continue that investment for the next years. And I will show you the roadmap. But I see that most of you have already heard about this. All this is not new for you, what I'm telling now. Is it something you already have addressed? Yeah, correct? Okay, good. Can I continue? And then this slide might be interesting because take a look to the picture. So you see circuit depth, circuit width, as I already said. And you see here a couple of abbreviations or acronyms, ZNE and PEC, that stands for zero noise extrapolation and probabilistic error cancellation. So what we do is with certain mathematical techniques like extrapolation and like with distributions, we try to compensate for the errors, for the noise. And you can do that in a smart way. By extrapolating, like in numerical analysis, you can calculate optimized results. And also with probability, you can find the more probable solution. And there you can reach useful depth and width up to 100 qubits. And so, meaning even if your hardware is not perfect yet, you can already increase the depth and the width of your quantum circuit so that you get to useful outcomes. Yeah? So that are techniques that we are using more and more. So, and that is what we call quantum utility computing. That is the next evolution. And then here, I will not read these details, but what I would like to show you is the number of qubits, 125, and number of gates. And these are all experiments where we see almost very accurate calculations with quantum circuits, with an increasing number of qubits, increasing number of gates in different experiments over the world. So where we see that we have really reliable outcomes, even better outcomes than with classical computers for these types of problems. So, and done in different scenarios and use cases. Okay, so what we then do is by zero noise extrapolation by probabilistic error cancellation and also by Pauli twirling, another technique, we get to this one. So if you would have said we follow the evolution of the quality of the qubits, okay. By 36, you would have 100 qubits, useful qubits. Now we jump really and make a jump to 100 useful qubits and thousands of useful gates in one jump, we could say. And this was announced in December 23. So we have really made a huge progress in the last couple of months. So we're doing useful quantum computing. And okay, that is. I will. This is another way to tell it. We say, okay, 100 qubits. That's a little bit the minimum to do real useful quantum computing. Are we going to do that today? No, we don't have the time to go to 100 qubits today. Our exercises will go up to 5 qubits with several gates. But the concepts we are going to discover today to do that and try them out. Okay, that's interesting. And this is something I would like to tell also as an introduction. We recently did ran our quantum summit. So each year we do a kind of huge conference in which we announce the announcements, and I would go over them. The first one is the Condor processor, meaning we have now 1,121 qubits on one Q chip of this size. High density, but reliability not top. But we master the art of the density. The second, and this is, some people say this is even more important, although we only have 133 qubits on the chip, we have almost full fault tolerance Q chip, because what is happening there, we don't have predefined connections between the qubits because they generate too much noise. We have dynamic coupling. So when two qubits need to be entangled in your circuit, then I didn't repeat superposition and entanglement in my introduction, but when they need to be entangled, this is done in a dynamic way. By the way, do I need to repeat entanglement? I forgot to tell that, but that is known by everybody. So one qubit status influences the state of another qubit. And for instance, the C0 gate is a typical way to do that. We will discover it in the exercise. So, but this is really a spectacular progress. And of course, we are going to combine both in the roadmap. We have now quantum system 2. Previously, we have system 1. What is special there? The modularity. We can connect multiple quantum computers together by long distance connections. And you say, okay, what is special? Don't forget that our quantum computers, superconducting transmitters, require a cooling to only a few millikelvins. And meaning that at this cold temperature, the system needs to work in a cryogenic environment. But that means that also the connections must be able to support these low temperatures, to keep the quantum effects between the computers. So we need to connect Q chips, QPUs, systems in the good situation so that the quantum phenomena stay alive, you could say. You understand? So, and in that, we now collaborate with a new supplier of cryogenic equipment, Blueforce, a Finnish company. In the past, we built our own cryogenic equipment. Now we are working with a partner to do that, to make that possible. I will tell you more about the roadmap in a couple of minutes. Qiskit 1.0 will come back on that in the exercise. You see 1.0, it is now intended to be on an enterprise level. In the past, it was pure open source community. But there were not hard and strict rules about the evolution. Now we say each year we want a new version with backward compatibility. It's really a professional, it's going to become a professional software while still being open source. But we want to make it ready for the enterprise and for utility scale computing with reliability, with support, with, yeah, as we do with all the, as you see with all the types of software. So, but that means one disadvantage, I have to be honest, if you migrate now if you would like to migrate to Qiskit 1.0, it's not possible. You need to reinstall it over again. So it's a complete new set of libraries, a new approach. The concepts are the same, but the installation is different. And once it is installed, it's more stable. So it's a new approach. We see also Qiskit patterns and Qiskit serverless, meaning we want to make that step two, to open it to the quantum computation scientist. You all know data scientist. We now talk about the quantum computation scientist, the people who are going to take their domain of expertise and use quantum computers to do something to make their to practice their domain of expertise. And this is also done with the Qiskit patterns, in which you say, I translate a problem from a classical problem to a quantum problem. I do the optimization with the Qiskit transpiler. And a transpiler is the alternative to the compiler. It's going to translate your circuit in an executable circuit. We will also discover that. Then we will execute it and interpret the results. So we also see evolution to job, iterative, and batch. Job, that's just the execution of a circuit, what we are going to do today. But we also have iterative. What is iterative? If you take quantum machine learning, quantum optimization, often you see that the execution is in a kind of loop, iteration. And in the past, you always had to, let's say, reinitialize your connection to the quantum computer. Now we see that iterative problems, you keep your connection, and iterative problems are solved more quickly. Batch as well, offering quite some circuits to get solved. And another interesting evolution, AI. Indeed, in our compilation, we have built-in AI, reinforcement learning, so that the transpiler learns from the previous work. How was the execution after my transpilation? It went fast. That's a good way to do the transpilation. No, it was not so fast, so I have to adapt my transpilation. So built-in AI in the transpilation process. We don't see that, of course, at system level. But what we are also working on is a code generation tool, meaning we have a quantum computation scientist who understands quantum, but he doesn't or she doesn't have the time to learn all quantum computing details. By just specifying with natural language what she or he wants, the necessary code is generated. So code generation tools based on generative AI for quantum. That's also what we're working on in Qiskit. So generative AI, quantum, they find each other in the evolution, you could say. And then a couple of other things. Then we are almost ready for setting the scene. I will not cover these things. I'll come back on that a little bit later on that one. I just want to tell you about this. We are not going to cover today quantum safe. What is quantum safe? That's a completely different story. That's about cryptography. What is the cryptography that is resistant against attacks by quantum and classical computers? Because our current cryptography is in danger. Because the algorithm of Shor is able to do some job, some work that we assumed that would not be possible to be done by a computer, like factoring an integer in primes or solving the discrete logarithmic problem. Can be done with the algorithm of Shor if your quantum computer is powerful enough. But there is a potential danger. And so a lot of asymmetric cryptography, which is based on this assumption that factoring integers is not possible in a reasonable amount of time, or solving discrete logarithm is not possible in a normal amount of time. Yeah, that is completely put in danger by the algorithm of Shor. What we see today is that there is a completely new generation of cryptography, and that is based on lattices, mathematical lattices, lattice cryptography, and lattices are subsets of the relation, the R to the power n. Real numbers to the power n. We have a lattice is a subset, and we have a complete mathematical theory behind these lattices. And it is possible then to create cryptography that you cannot decrypt, not with the classical computer, not with the quantum computer. Yeah, although we think it is like that. There was not yet smart people that were able to decrypt them. And there are some algorithms, the crystals Kyber algorithm, the crystals deletium algorithm, that are quantum safe, and that are implemented more and more in systems. And you say, yeah, this is hype. No. If you take in the US, the White House has said by 2030, between 2030 and 2033, all our national agencies, so agencies working for government, must implement quantum safe algorithms. You might say, why? Because criminal organizations, criminal states, they can say, harvest today, decrypt later. They can store our current data, our current passwords are used in the internet and all types of equipment, nuclear plants, planes, which have all sorts of cryptography, and they can decrypt it later. So, and get access to useful assets, IT assets and operational technology assets. So that is why in the US, of course, they are really a little bit, they have said it must be already be quantum safe in the next 6 to 10 years. But we see also in our country, the financial services companies and the telco operators looking at quantum safe. But okay, I will not, that's all I think. If you would be interested in the quantum safe story, just let me know. That's a completely different topic, because you don't need a quantum computer for quantum safe. You can implement quantum safe algorithms without a quantum computer. You can use a quantum computer to try it out, but they are not powerful enough yet. Okay, so okay, use cases. I will skip this and take this slide. What are the use cases we find typically for quantum computing? 3 big categories: simulating nature, indeed. Think about chemical reactions that we want to simulate. A couple of use cases: develop new batteries, recycle batteries. Develop vaccines, medicines, carbon capture materials, things like that. A middle level here is a complex data structure. I also would add to that quantum machine learning, AI, and then search and optimization, optimizing certain problems. And all sectors are optimization problems. For instance, I got the question recently from a company with an IT department, as our companies, but they have tens of projects, they have hundreds of IT professionals, all with their own skills, with their own working conditions, labor conditions. They have deadlines, they have budgets, they have rooms, they have facilities, and bring that together so that all requirements of the company are satisfied, IT requirements, in an acceptable amount of time at minimal cost. while everybody is working at his full capacity. So that's kind of complex optimization problem is where quantum computing can come in. And you see here a couple of examples of companies. What do you typically see there? Large organizations. Think about Boeing. Boeing is looking at quantum computing to develop new materials that are more solid and yet lighter, or with less corrosion, to give an example. Other examples. ExxonMobil is also taking a look at optimization problems, navigation optimization of the ships with LNG containers, liquid natural gas, and so on. So all these, you see quite some examples here. What we also see is, and it's something I need to tell you. You see on the chart, QIC and QCC. QIC stands for Quantum Innovation Center, and QCC Quantum Computation Center. Indeed. What we are going to do today is working on quantum computers in the cloud, and that is still the major set of cases, meaning that quantum computing today is essentially cloud computing. We have, and these computers today are in a data for IBM are in a data center in New York, not far from New York. But we also are going to start a quantum computation center in Germany, in Stuttgart, not far from Stuttgart. Why? Because first of all, we must. There is demand for the capacity, so we need to start up an additional quantum. A little bit also on another place than New York. And secondly, we have a lot of European clients that are sensitive to the protection of their intellectual property. They say, when it is in the US, can you guarantee it is not abused, it is not used? And so that is why we can, of course, sign a contract. Nobody will use your intellectual property. But for the perception, we have said we are going to set it up in Germany, where there is already also a lot of experience. That's the cloud. And then you have also some companies, like you see, Tokyo University, Rensselaer Institute, Fraunhofer, where they have their own installation also. They have installed their own quantum computer. Fraunhofer, Baden-Württemberg, there they have done that for supporting the Fraunhofer Gesellschaft, a scientific institute. Money was coming from Baden-Württemberg government, from the federal government of Germany, and also some sponsoring companies, because it is not some, because of it's not a kind of server that you put in a room and you start it up. No, you have to build your cryogenic situation of equipment and context. It is really labor intensive today to set up a quantum computer in your computing center. So at this moment, so another Basque in Spain also, they really believe strongly in quantum computing, and they are going. They are now setting up their quantum installation in Basque country. So, and then you have quantum innovation centers. There you could say it's a combination of companies, universities, spin-offs, startups who believe in quantum computing, do research together and solve certain problems with quantum computing. And they have use cases they work on together. And of course, they can run on the cloud. They can, at a given moment in time, go to their own installation. But, okay. I already explained this one. Again, a kind of scientific explanation here, scientific and more. The content one, that is this graph. I would like to explain. You see here circuit complexity, increasing circuit complexity. You could also say problem complexity. And you see the cost, meaning what does it cost in time, in resources. It's a little bit a general approach, a general philosophy. And we take the light blue curve to see classical problem. So when your complexity increases, you see an exponential growth in cost for certain types of problems. Not all of them, huh? But certain types of problems, there are exponential cost. There is an exponential growing cost. You see that the computers we have today, which are still noisy, as I said, the noisy intermediate scale quantum devices, NISQ, we call it often, NISQ. You might already have seen that. NISQ. They have this, let's say, approach. The complexity grows. They also see growing their cost, but not so spectacular. And then you have the straight line. That is when we have full fault tolerant quantum machines with full error correction, where we are not yet there. Yet you see something interesting. You see that ideally you follow this curve and you solve your problem. You see? So there is reason to use quantum computing, even if there is not yet a fully corrected quantum computer. That's what we want to say with this. The goal is to do already useful things with systems that are not fully noise-free. That is what we say here. And we also see scientists developing algorithms, knowing upfront, my system is not correct, so not completely working full fault tolerant, but I create an algorithm that takes that into consideration. And in that algorithm, they get on a solution, and at the end, they do some error correction techniques. So, or in the middle of the algorithm, they do already error correction techniques. So, but that is taken into consideration. So I hope this is also meaningful to tell you. So, by the way, in quantum machine learning, you will see types of algorithms in the blue and in the black. So two types. Okay, one of my, and then I think this introduction is okay. Yeah. Interesting to notice. What are we going to do today? We will be on the left-hand side, open plan, free plan. But you have systems up to 127 qubits today. Last year, when I did the presentation, we had systems of 5, 6, 7 qubits for free. Now we have 127 for free. The only problem, no service level agreements. So we will make an exercise, launch an execution on a real device, and I hope that you will see the result at the end of the session of today. If not, take a look tomorrow, you will see your result, because you will be put in a queue, wait your turn, get your result. Okay, suppose we have people that say, I would like to have better service, meaning that I want the system to be available more and higher percentage of the time. Then you can go to a pay-as-you-go approach. Then you have access to more than just 3 large systems, and you pay $1.6 per second. Don't be afraid, it is really the execution time on the machine itself. So all the transpilation, interpretation at the end, that is on the classical system. The transpilation is done by a classical computer. So that is not included. But of course, it is a quite amount of money if you have, for instance, 100 iterations in your optimization algorithm. Can quickly, for a moderate company, it can quickly become too expensive if you do a lot of work. But okay, it exists. There is a need for it for people who are making the transition from really experimenting to really more professional use. For the companies who believe in it, I would say we have the premium plan. That is, then you pay a certain amount of money, and I will give you an indication in a couple of minutes, for what we call the quantum allocation units. You could say, I want 100 hours of guaranteed access to 2 quantum computers in a period of 28 months. Or can be 100, can be more than 100 hours. That is number of working days. And so yeah, you pay a certain amount of money. The amounts of money are not so low. I have seen amounts there, and I'm not a salesperson, so I cannot say what the exact figures are, but the order of magnitude can be from €250,000 to start with, so to several million, depending on the needs of the company. So it's not for the small and medium business anymore. That is already for the larger companies who say, I want, strategically spoken, go for quantum computing. Like that. And then the dedicated service, and that here you can use quantum computers in the cloud, or that the complete fleet is available. Or you can say, I want a system completely for my own, in the IBM data center, or in my own data. The quantum computing center is better. Data center is not a good name, because quantum computing is not about data, it's about computing. And then you have what we call a dedicated service, and there the price is to be discussed. That is not made public. So, perhaps quantum learning, and we are going to take a look to some elements of quantum computing today. Of course, there's so much more. Look, we have books about quantum courses, Udemy courses. I see a lot are doing a lot in quantum computing. But we have also a nice platform, quantum learning platform, also for free. Why does IBM want to do that? Because, of course, we want to make a lot of people attract them to quantum computing, that they want to learn about it. So, because if you have people with skills, yeah, you can. It's better than you can do more. Your market impact is better, of course. And this is a platform where you can do quite some learning. So, if you say after this session, what I already know, I want to do more, starting from zero, and I want to become a hero from 0 to hero, I would say. Yeah, you have a quantum learning platform where you find all courses. You can even do a certification. You're updating that certification. But, you have tutorials, meaning you have exercise examples that you can try out and learn from and so on. Yeah. So yeah, this is also a slide that I am at this moment. Yeah, and it's of course the current situation. It's an IDC. It's a little bit publicity. I know this one. It's marketing, but okay. We are at the moment the leading company in quantum computing. Of course, I always tell that in 2 words today. I say, because things are evolving on the hardware level, on the software level. We try to do both. That's why we are leading. We do a lot of research in the hardware area and in the application and software area. One of our, if you would like to do that, also yourself research in that area, the place to be at this moment also is Zurich in Switzerland, where we have a lot of research going on around everything on hardware and also everything, more than just quantum, because we're also developing chips there that have built-in AI on the chip, hardware AI, you could say. And also a lot of research in the use cases. If at a given moment in time, I can always invite some of our fellows that are working there, and they could come to here to meet you. I can always, recently we had a visit from a lady from the Zurich Club, and of course, yeah, always interesting when they give a speech. That's okay. Yeah. Yeah. This is a roadmap. One of the things that also are interesting to notice, and then I think we're ready for the exercise. what you see in the roadmap, it's a hardware roadmap. And you see the Heron processor already mentioned, and you see between parentheses K, 5K, 7.5, what is that about? That is the number of gates. So meaning, I take a look to 2028, flamingo processor, 15,000 gates of 156 qubits, but we can connect them to 1,092 qubits. So meaning that in 28, we will have a system of 1,092 qubits on which 15,000 gates can be executed at very high fidelity, reliability. We believe at this moment still in superconducting approaches. We follow the other ones, but I think we have the most promising roadmap at this moment in time as far as number of reliable qubits and reliable gates is concerned. But things can evolve daily, we know that. At this moment, I dare to say that. And you see even that in 33, 10 years ago, it's quite a lot, a complete error correction on 1 billion qubits, miljard in Dutch, billion, and 2,000 qubits. Yeah. And then, of course, we are going in the direction of millions of qubits. That's the road. Huh? So this is the roadmap. This is, yeah, you must also know IBM is always a little bit a risk-averse company, that we are always afraid of telling things that are not correct. A lot of governance also on us. We are not allowed to tell things that are not true. And so when we tell this, we might be sure it will happen. So like this. Of course, there might become competitors that say in 33 I have 100,000 qubits and 10 billion gates. Okay, that might be, but at this moment we don't think there is anyone able to do that. Huh? But everything can change, of course. Okay, Qiskit, I will be introduced, and then we are going to the exercise. And why is Qiskit so interesting? First of all, we call it it is a kind of lingua franca, we say, for quantum computing. About 70% of the quantum developers prefer Qiskit. We have also alternative technologies to Qiskit, alternative types of syntax and approach, but at this moment is the most popular one. It's not a lost investment because not only IBM quantum computers, but also in total 8 types of technologies are supported by Qiskit or support Qiskit. Meaning that if you learn Qiskit, you will be able also to access Rigetti computers, one of our competitors, or Amazon, also a competitor. They're also working on. Of course, they don't have their own hardware. They use partners for their hardware, but they have a kind of platform to access quantum computing. And Qiskit is also supported. Yeah? So not a bad investment, I would say. So it's a way to have a kind of universal. And then I stop with this slide. You might say, what is that about? You see, the interesting thing is 2093 research papers. So research is continuously going on in the area of quantum. It's an interesting domain because it's intellectually interesting. It combines multiple disciplines. Yeah, and what you typically see in these papers is what is the problem we want to solve? What is the classical approach? What is the quantum alternative? And what is the speed up with quantum? And how can we then do it in a real device? And so that is often what you see in these research papers. And they are publicly available in multiple domains. So always interesting thing to study. And also good basis for a master thesis if you would be interested. I've been guiding some students from multiple, some universities, and often we start from a research paper, and then we say, okay, this is the starting point. I always set the expectations. Some people come to me and they say, I'm going to develop a new quantum algorithm. I say, oh, that is, how many years do you want to invest? Okay. We are just doing a master thesis. You have 1 year. Try to understand the article, try to elaborate it, apply it, try to understand the underlying other articles and make a nice story of it and apply it in new situations. Okay, but inventing a new algorithm, it might be, but not so easy. So, okay. Okay, that was my short introduction. And then I go again to my table of contents. Other questions at this moment? Is everything okay? Isn't it too easy? Okay for you? Just let me know. You say you're losing time. Tell me. Okay. I go to the next topic, and that is quantum computing systems. And Jago and the team asked you to stop share my screen, to make an account, and that is what you're going to use. I will go to my browser and share my screen. Share my screen. Share second. I will take my complete screen. The NS Teams?
Yes.
Great. Yeah, okay, great. I start from scratch and you already have got the instructions to log on to the system, but in case you would not have the URL anymore, it's not difficult. You say, IBM Quantum. And probably the first thing is okay. And I have really start from this one. And you could use even your Google account, you can see, or your LinkedIn account, or your GitHub account. But you can also use an IBM ID, and probably most of you have already succeeded in using that. Yeah, okay. And I will also do that. I will come now to a single sign-on screen. You will not have that. I don't mind that because I have ID working. This should be and the first thing we are going to discuss is go to the compute resources. And I will stay now there because otherwise I need to run too much. Compute resources. And what you see here, I will go to the case of the Osaka system. First of all, nice to know, how is this system installed in Osaka? No, this is installed in a IBM Quantum Computing Center in the US. Yeah. I already, by the way, asked, why isn't there an IBM Brussels? But yeah, I am not, don't have enough influence to select the name. But yeah, so there is, by the way, you see here, nice to know, after the start of the war in Ukraine, IBM decided to create the system IBM here. Just a small anecdote. I go back to the resources. When I click on it, I find some interesting parameters. That's why I want to do it, and as such we learn. You say, first of all, you see total pending jobs 390. So if I would now run a quantum circuit and execute it on that system, yeah, I have probably my result in 2 hours. So you will see, perhaps it might be like that. Okay. Then we also see basic gates. Indeed, we are going to use in a couple of minutes gates on our circuits, but you could call them logical gates. Gates that are really containing the logical thinking. When they are executed on the system, there is a transpilation process, a compilation process that will take a look, and that will use only 5 gates, basic gates that are implemented in the hardware. You understand? So the transpilation is going to translate my logical gates into physical gates that are really executed. And I will show you the effect of that. You also see here median T1, 264 microseconds, meaning that, what is T1? T1 is the time between, is a decay time. Sorry, thank you, Jan. I probably put I often forgot the pencils, forget pencils as well. So what is a T1 time? If you put your quantum bit or qubit in state 0 and you do nothing, you wait, then it automatically decays to the ground state. And this happens on this system in about 276 microseconds. You might say this is not, well, this is fast, correct. First of all, there is seriously worked on that. We have now systems up to about, I would say almost 1 millisecond. So 5 times 4 times. And that's the first thing. And of course, the executions of the quantum gates is done even much more faster, an order of magnitude faster. We talk about orders of nanoseconds. So, but okay, this is of course a problem. That's a problem of the noise that is subject to a lot of research, as I already mentioned. But this is documented. We have also median T2, that is the superposition state that decays to 0, but this is something we still need to learn, the superposition state. And then also interesting, because I mentioned it, is the following. If I go a little bit lower, you see this. What is this about? You see qubits, numbers, and if you see 0 to 126, and you see connections between the qubits. And not everything is connected with everything. That is a weak point of superconducting technology. If you connect everything with everything, the noise would be too high. It's a trade-off between, let's say, the noise that you don't want to become too high and functionality. Because if I want to do a C0 operator, or an entanglement between qubit 20 and qubit 41, for instance, they are not directly connected. So what the circuit needs to do is to build in a kind of swap operations. Swap, meaning I change the function of my qubits so that I rewrite the circuit so that both qubits change their semantics and I can have my entanglement. But of course, swap operations take a lot of time. So that's why you see regular places connections. And that is now what I wanted to say also with my Heron processor. In the Heron processors, this will be eliminated. There will be dynamic coupling to eliminate so that to save time and to save noise. So but at this moment here you see it's an Osaka system. You also see open Quantum tree I see now. What is Quantum? Quantum, and you will discover that also later on. That is quantum assembler language. Some people might have even programmed assembler on the old computers in the past. It also exists in quantum, And the language is Open Quantum. It's a kind of standardized language. The syntax is understandable, but really close to the gates. Okay. That was the system. Yeah. And also need to tell you about something else, and that is simulator. Quantum simulator. What is that about? So I already told that. So we have the real devices, but we have seen the disadvantage, the Q. We have also simulators. What is a simulator? That is a classical computer on which we have installed an emulation software that mimics a quantum computer. So why? Because if for people who are going to do learning, or people, even quantum developers, before running on the real device, which costs perhaps too much money, I first test it out on my simulator. And if everything is logically correct, then I run it on the real device. So that's the approach. And of course, a simulator, as you can see, I don't see any P1 here. That phenomenon is, of course, not existing. Everything is correct. And I see my gates, you see, 30 gates. Of course, there is no transpilation to be done. The transpilation is the same. So there are no physical, let's say, gates. The transpilation is basic. And not so much jobs because they are executed immediately. So, that's a simulator, and we are also going to use that. Okay, that is a little bit my introduction. The only thing I wanted to show you now is our systems. So some of you will see there are more systems in the cloud than the three that we have access to. This is our systems for paying clients, and clients who pay money for pay-as-you-go or the premium. They have access to much more, a larger fleet of systems. Okay. You see also maintenance, indeed. When the computers are used for a certain amount of time, noise becomes more and more impactful. Results are not so correct anymore. And then the system needs to be recalibrated. You could say reinitialized to work again correctly. So that's why sometimes you see much more often maintenance than in a classical system that we use today. Okay. Still interesting? Yeah.
Could you tell us a bit about the other two characteristics on the and the other is how many operations?
Very good remark. I forgot that. We have indeed three interesting parameters, as Professor says. Qubits is the number of qubits. EPLG is a new one. Error per layered gate. Meaning, I will make a very small sketch of a circuit. Suppose you have 4 qubits, Q0, Q3, and you have gates, and you have a layer, and again a layer, again a layer, again a layer, and measurements. And this is an expression of how many errors you have per layer in your circuit. The lower the better, of course, but it is on average. So you see that the Sherbrooke system is, for instance, less noisy, I would call it, than the Brisbane system, and much less noisy than the Quebec system. So it's an error per layer gate. And the third one, CLOPS, is also a very interesting one. That is the abbreviation of circuit layer operations per second. Circuit. You all know the term FLOPS from supercomputing. Floating point operations per second, an indication of the speed of a high-performance computer. The higher, the better. And we also have CLOPS, circuit layer operations per second. Again, how many layers can you execute per second? The higher, the better. This will become very interesting when we will have real-time quantum computing. Today it's still, okay, we are in batch, If it takes 3 seconds or 4 seconds, are you going to comply? No. Complain? Huh? No. Of course, in the future, when we have real-time quantum computing, when you are behind your laptop and you want immediately a response, then this becomes really critical. And the speed of the circuit execution becomes important. And we are working on that. At this moment, we have systems with a maximum number of flops of 15,700. So these are not the most fast ones you can see. We have systems that are 3 times fast.
So with the 5,000 plots of 5,000, it still means that for one layer in 200 microseconds, which is comparable to the decay of a qubit. So how does that?
Yeah, then I also need to calculate to do the calculation. If you have, yeah, I should calculate. I should also verify the calculation. That is really possible. They will a couple of minutes to figure out. Good question. Yes, it's a good remark. You have to that number of microseconds that is indicating the decay. Of course, important to tell. Even if you're T1, you know the T1. Suppose I make that 300 microseconds. It will prohibit you to continue your calculation, but your calculation will be less reliable. You will not be stopped. You continue to run, but it's your responsibility. The result will be difficult. But yeah, if you could, I will do the calculation. It's a good remark. Yeah. Okay. Good. Yeah. I think we are ready now for the first type of exercise. Take a look at this watch. And I would like to invite you to go yourself to the Quantum platform. If not yet done, I see a lot of people that already have done that. And then what you can do, and you can follow me, is go to the what we call the Quantum Composer. And the Quantum Composer, and I will start from scratch, is this. Oh, yeah, sorry, new file. I will make a new file. You should have this one. What you see here is 4 qubits, an empty circuit, and this is an environment where you can try out your circuit. Not yet execute immediately, although it is executed online on a simulator, but you can try out some gates, and the gates are at the left-hand side, and you can also decrease and increase the number of qubits. You see that this the measurement. The measurement of the qubit will happen in a classical bit. See. If I'm telling things that you already know, just tell me and I go faster. The first tryout is a classical operation, you could say. It's a knot. And you see, for people who would not yet know it, and we have what we call probabilistic computing. And you can see that here. Probability 1 at 100%. What is also something that you can deduce from this? You have Q0, Q1, Q2, Q3. So the least significant qubit is Q0. The Q0 is here. You see? And I will make that even more readable by deleting a qubit. Let's see that. I delete the qubit, I delete. Yeah. And you see that I have 001. So we, as in Qiskit, we use the classical notation. You know, what I mean by that is, if I write, for instance, 101 in binary, that is 5. Of course, we keep that, let's say, way of notating the qubits. Q0, Q1, Q. So if you have this sequence of qubits, it is Q2, Q1, Q0 that you write. Understand? So important. Why do I tell that? Because in some scientific articles, I have already seen authors who use the other sequence around. And for me, that was very confusing because I once was reading an article and what is that? I didn't understand at all. I didn't understand immediately why it was like that. So, but then I saw that the notation was otherwise. This is the notation we use, and I like it the most because it's really compatible with our decimal notation, with our binary notation. So we also do that in qubits. Okay, by the way, and now a small little bit of explanation as well. If you have one qubit, it can be a linear combination of 1 and 0. But if you have two qubits, for instance, you note it like that. And now, what is that mathematically the meaning of that? That is, of course, a tensor product of qubit Q1 and Q0. And when I write this in mathematics, it's like that. It's a tensor product of two unit vectors, and the tensor product is a four-dimensional vector. So two qubits, 4 dimensions. And when I would write something like this, this is the tensor product of two qubits. And it is, in this case, easy for me. I have to think that I think this one. It's also a column vector, but of 8 dimensions. And so with each qubit, you double the number of dimensions because adding a qubit is adding a tensor product, is doubling the dimension. So, and all these operations you find here, you can say there is a matrix representation. So it has a mathematical equivalent. And we'll come back on that in a couple of minutes. So, okay, so still with me, it was still okay on everything. Okay. Yeah. So it's now go to reporting. What do I see? I have applied 2 times not, okay, but I do 2 times not. Yeah, the impact is 0, of course. But you also see probability, meaning that what I put there in the circuit is a specification of experiment that needs to be done. So this circuit is executed, for instance, 1,000 times. Each execution, we get a result and we measure, and we make a histogram, we make a probability. Then alternative representations as well, but let's stick to this one today, the probability, meaning that it is probabilistic computing, not deterministic computing. You do an experiment a number of times, you measure the result, and then you make a statistical representation. Yet it is still, and with this result, you can still do useful computation. That's the goal. Okay, that is the next thing. Now I'm going to do interesting things. And this, the first one is my Hadamard gate. Because this is the superposition gate. This is the gate that creates a state that you don't find in the native hardware of a classical computer. You can simulate, but it's not built in the hardware. And the Hadamard gate, you can see I have probability 50%, 0 and 1. So when I do an execution and I measure, in half of the times I will have 1, and the other half of the times a 0. Yeah, understand? So that is what we call superposition. Why is this interesting? Because this can create a fantastic starting point for an algorithm. Let me explain. If I say I have Hadamard and again a Hadamard, this is the power of 2. You see, I will please. Okay. You see, I have 3 qubits I apply on each qubit the Hadamard gate, and you see I have initialized 8 states 2 to the power 3. And that is what you see often in a quantum algorithm, that this initialization with one or several qubits with the Hadamard gate. You create superposition, because then you have that parallelism, you could say. You have a qubit in several states at the same time. Yeah? So that's the big advantage. I think I can even add it again. Yeah, okay, and I have 16 starting. You can imagine it. So I can work with 16 states at the same time. And of course, now the goal is to apply smart operations, measure in a smart way to do something meaningful. But okay, and we will do that now with the second gate, and that is the C0 gate. And first of all, delete my qubits to make things easy. And I even add my my second qubit, and I delete that gate, and I use now this one. This is the conditional NOT gate, which is creating entanglement. Meaning that the qubit Q0 influences qubit Q1. This is information science, but in physics, and now I'm going a bit, perhaps any mistakes, but you know that this is the Einstein-Podolsky-Rosen paradox in what we call in entanglement. So one particle influences another, even on a distance that we cannot, a large distance. A phenomenon was described in 1936 already, I think, and that was discovered in the 70s and some European nuclear.
Will it be necessary to put a Hadamard on qubit 0 first before the 0?
Yeah, I can do that. I'm going to do that. I'm going to do that. Yeah, indeed. I will create that. Yeah, certainly. First of all, I start with that one. Because I will learn you the mechanics of the C0 gate. If I do, first of all, the small bullet is the control qubit. The large cross is the target qubit. And when I change, I will take another target qubit now, and we initialize it is 1. Okay. You see the impact? What is the impact? Nothing. You see my control qubit is still 0. Yeah, remember this sequence again? That's the sequence. My control qubit is 0. My target qubit is 1. Nothing happens. But when I change my control qubit and I give it the state of 1, then it changes the target qubit. You see, the target qubit becomes 1. And when the target qubit was 0, it becomes also 1. You see that the control qubit manipulates the target qubit at once, instantaneously. Now I'm going to do what the professor suggested. That is, I'm going to combine these two gates. I'm going to use my Hadamard gate, which is in 50% from the cases will generate a 1 and a 0. And of course, I see immediately the impact on the target qubit. 0, 0, 1, 1. Does everybody understand this? So yeah, this is important to understand. And this is a famous state. This is the Bell state. Bell, who was the first gentleman, he did this really in the hardware. Now we have it easy to do, but you must imagine when quantum computing was really at its infancy, or even before, this was not a straightforward thing to realize. Huh? So And now we are going to do the following stuff because I'm still playing now, and I'm going to do real execution. And I use my measurements. And as learned before, measuring means that I'm going to, let's take a look to the time because measuring means that I'm going to take my quantum state and collapse it to a classical bit. Okay, now I'm going to execute, and I'm going to do that in two ways. The first execution, set up and run. I will use the quantum simulator. We use that to see that quantum simulator run as a quantum simulator, and it is run. I will go to the second thing, and I invite you to do the same, set up and run, and I go to the quantum computer. And I see, Osaka. I will select Osaka because in Brisbane and in Kyoto, the number of jobs is even higher. Yeah, just try to figure out and make it at the warning because we didn't get it before, to be honest. But okay. Okay, let us see. I will not guarantee that we will have a result today because there's a lot of work activities going on. But I will show you now. The first one is completed already. You see? The first job is completed already on the system. But it is also on the simulator. And you see the results. The only remark you might have here, there is a statistical difference indeed. I don't have twice the same 50-50%. That's like if you take a coin. If I throw a coin, in 50% of the cases, it might be 49-51 that you have had and there. You understand? So it's not always exact. The higher your population, the closer you get to the 50-50, you know that. But yeah, probably I should have increased the number of shots to have really that 50-50. But you see there is a statistical difference. Okay, when I would execute, sorry, before I do that, I go down and I see here program, the diagram that is used. Nothing spectacular, I will say. I go back to my dashboard. I go back to my quantum composer. Jobs, and I see that when I take a look at my other job, it is in the queue. And the estimations working correct. But I go to the previous execution from my side. Sorry, I'm not doing the right things here. I'm using jobs. You see here, I'm going to show you something that I executed on a real device a couple of days ago. You see, I'm going to select this one because this is still in the queue. Same for you probably. But I invite you later on today, perhaps even at the end of the session, to take a look, and then you will see like this one. And I will take a look now to that execution. You show me the difference. I go, for instance, to this one here. First of all, interesting to notice, while it should only show results 0, 0, and 1, 1, I also get 0, 1, and 1, 0, meaning errors, noise. And you see the system is not working perfect. If it would have been recalibrated and I would have run it immediately, you might have here perhaps a very small error, but you can see this error is not so small anymore. Of course, I can still deduce the right results. But suppose I would never reinitialize the system. Suppose the maintenance people have holiday and nobody is doing anything anymore on the system. Then at a given moment in time, yeah, I would see no difference anymore between the four possibilities. Understand? So this noise increases when using the system continuously, but that is why it is reinitialized. Another thing interesting. What you see here is a transpiled circuit. So my circuit with the Hadamard and the C0, you don't recognize it anymore. What you see are the physical gates, the 5 physical gates used. Moreover, and if I would need to go down to find my measurement, why? Because I have a system of 127 qubits. I'm not using, you see. This is the transpiled circuit. I use 2 qubits out of 127. You see? You understand what I want to say? Another thing I did not show you is the quantum. That is on the right-hand side of my interface. You see this coder. This is the quantum coder. This is created automatically when I make modifications here. But I can also work in the other way around. Suppose you have some nice code written in a text file, copy paste here, up, and you will see immediately the impact on the graphical representation. It's also possible. I suppose you have worked. I'm happy. Instead of I want to keep my code, some people like that, okay? Because I want to port it to someone else or something like that, I can copy paste it and reuse it later. Next one. I'm going to create another state, the dot state was famous. I'm going to create another state. Oh, sorry. I'm going to sorry for that. I missed it because I'm starting behind. Okay, I start over again. And I go to my other map gate. I go to my bell state, and I add now a second CMOS, but I edit it, and my target becomes Q0, Q2, my apologies. And you see here another type of circuit, which is super entangled, and you have 0, 0, 0, and 1, 1, 1. 50%. We should understand this as well. This is also a famous circuit, the GHZ circuit. It's the abbreviation of the names of 3 gentlemen who have implemented this in the hardware many years ago. And this is also relatively famous. Everybody with me at this moment? Yeah, is it still doable? Yeah, not too easy, I hope. Okay. Let me take a look. I wanted to show you. Taking a look to my. Okay. Now I would like to ask you the following. You see here a circuit. Could I please ask you to create this circuit yourself? This is a diode. This is the dotted line. And you can try it out, and I will show you the result. Does someone know what we are doing here? Also interesting. And in order to learn, to discover what you might be, what you are doing here, you can try out here XX, nothing, then you will see what it is doing. So I give you, please try this out. So this is a new gate, a Toffoli gate. The Toffoli gate with 2 control qubits, and only if both are 1, the target qubit is modified.
So, Eric,
I don't see the X gates.
Wat wil je zien?
De export zie ik hier niet staan.
Die X is daar en dan.
Daar staat.
Ja, en dat is de. Ja, dat is die, het is deze, het is de tweede. Maar je moet eerst beginnen. Ja. Ja, die X, ja, dat is correct, goed. Ja, my apologize. Sorry. Indeed, the first one is the X gate. And I apologize because my copy paste is coming from Qiskit and you have the interface from the controller. So I apologize. Yeah, the correct question. This is not. This is the X gate and the X, simple X gate. Yeah? So
how do we produce a barrier?
Yeah, I will show you. So you drag in value from 1 qubit, and then you edit it. Yeah, it's a little bit trial and error in the beginning. Huh?
What is the X?
Oh, the X, yeah, this is okay.
Dank voor de foto's. Oké.
So, by the way, the barriers, what are they doing? Nothing, just for structure. Yeah. They're used to make it a little bit, the circuit readable. And you see, I have a kind of initialization, I have a kind of elaboration of the problem, and I have my measurement. You don't need the barriers, but when you can imagine when my circuit becomes large, it's interesting to have some logical structure, and then the barrier is used. And I will now go to will do it myself, and I will do some experiments, and then someone who knows what we are doing here can tell me. Perhaps you already know it.
Yes. But good enough. Hij is wel iets speciaals. Hij is hetzelfde. Ja, blijkbaar. Hij is S. Ik weet wat hij doet. Ze komen bij jou. Maar evolution is een not. Allemaal op z'n ogen. Nee, dat is exactly zo. Not so. I'm going to say you can say it. I don't know.
Ja, maar in dit geval is het een fatsoenlijke shotgun, maar ik ken hier wel tegen shotgun. Er is geen shotgun, dus ja, gezegd.
Ah ja. Wat we hier doen?
Engels.
Ja, wat ik
Nee, Engels bedoel ik.
Ah ja, ah ja. Als we doen is dat ja, in addition to, you can say addition to two qubits. And I want to say an important thing. There is a theorem that proves that every problem that we can solve with a quantum classical computer, we can solve it with a quantum computer. But we don't want to do it because it will take too much resource. Perhaps, so what you can see when the result here, 1 0 0 0. So then don't mind the original states. You see here the result. I have 1 plus what I have here is the following. I have added 1 and 0, and the result is 1. You can see another one. I have 1. The result is 1 0. So what I have here really is a small, a small circle that is doing the following. It's really the table of the addition of qubits. It's really this one. So 0 plus 0 is 0. And I should do it like that, of course. I carry over 1. So it is the decimal addition, you could say, what I'm doing here. When I have 1 plus 1, I carry over to the next. I have 1 plus 1 is 2, and 1 plus 0 is 1. That is what I'm developing here. The quantum adder, you could say. I add 2 qubits. I repeat, we are not going to use quantum computing to do this. That would have too much, require too much resources. It will never be as efficient as in classical bits. But okay.
So here the last gate, the double control knot. So this means that the 2 top qubits have to be 1, and then it flips the qubit.
Yeah, right. Yeah. Okay. Yeah. 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 Indeed. That is a Toffoli game. The Toffoli. The Toffoli gate is a gate that indeed, as you say, the 2 control qubits need to be 1, and then there is impact on the target qubit. If one of them is 0, no impact. Okay. We will take the break then now. It's okay. And any question of are we still doing interesting things? Please tell me. So, useful. Okay. Okay. Thank you. So as I said, let's take a break. I don't know how much we would like to do as a break.
Yeah, let's take a 5-minute break till 11. So you can go to the toilet, you can take some coffee, some cookies, and then we restart at 11.
In Quantum Lab, we are going to make our first application in Python in the cloud. This is very simple. I will sometimes use certain syntax that is really understandable. But sometimes you will need to accept some syntax, but you say, right, that is not so special, why is it like that? Yeah. For me, the same. Sometimes I say by myself, why this syntax? But okay, it has to do with the Qiskit library, the modules in the library, the functions. Yeah, it's typically a bit for the Qiskit world. In the beginning, it's a small threshold you need to take, but then once you are used to it, okay, you accept it. It's like every programming language you could say, or every framework that you work in. So, but I will now go to my desk and I will explain how we are going, and you can follow me. We are going to create our first program together. And I will explain what I'm doing. So I will justify my steps. Yeah. What we are going to create is again the belt state, Hadamard and C not A. And we are going to execute them on a simulator. Yeah? With Python. So the same exercise so that you see how it can be translated. And then next step will be something more difficult. Yeah? But let us take a look. So I go. You can go back a little bit down, and you see here Quantum Round. And this takes a couple of seconds because we need to have a launch a server. And the server is starting up normally. So this is the alternative to your own local installation. While I'm doing that, you can also install Qiskit on your own laptop. And then you can also use simulated and real quantum devices. Yeah? And you will need an API token to connect to the quantum computer. I will show you where you can find that, in case you would like to do that. We use that API token for authorization and authentication. It's a very long token. I will show you later on where you can find it, if you would look at it. First of all, let's now go to Qiskit one. We are going to use, that's the advantage, of course, of the cloud. You have the latest version, no installation burden, no issues, and I have an empty notebook. Everybody is aware, I guess, of Jupyter notebooks and no secrets for you. You might even be better than I in that, because I am with full-time programming anymore. Okay, and Qiskit. Import all. I import my Qiskit libraries. I hope it is visible. Otherwise, I can make it a little bit larger when we do that. It's better. I think. Of course, you will see less on the screen, but next step. Now I'm going to create two qubits. How do I do that? I use a variable name, and the variable name is free to choose. I use QR, but that use everything you like. But this is a keyword now. This must be correct. Register. Sorry, we can make typing because visible here.
Sure. Right. Sure.
Yeah, for the mic. Yeah. Okay. Okay. Yeah, for the mic. Yeah, great. So, quantum register. Yeah, I'm going to create a classical register. Classical. No, yeah. So now I have 2 qubits and 2 classical bits. Yeah. Then I'm going to create my circuit, and my circuit is of course a combination of both. So I have my circuit, but then what I like to do, because for educational purposes now, not in real life, because this would take a lot of additional time, I'm going to make a drawing, intermediate drawing of my circuit. So what I do is I import a matplotlib library. Yeah? You know that probably. So that you can make nice pictures now and then, in line, meaning within my notebook. And now I'm going to make a picture of what I already have. Of course, nothing special. MPL is the abbreviation of matplotlib, and I can use a certain style. I will use the style IQP, that stands for Interactive Quantum Programming. This style, why do I use that? Oh, it must be an X and equal to, of course. Oh, circuit draw, MPL style. Circuit, okay. I made a mistake here. Yeah, you see it's real. I'm not cheating. I'm really doing the right stuff. I will certainly make more mistakes because I am not fully concentrated on the coding now. You see an empty circuit. Yeah? There is nothing in it, but I'm ready to do something meaningful. I can now create my first gates, and I will do that, of course. Oh, well, the circuit, Hadamard gate. What am I doing here? I create my Hadamard gate on qubit Q0, QR0. You understand? So on the first qubit, it is number 0 in Python. I have an indexing starting from 0. I have my first Hadamard gate. Yeah. And I will see, and I will copy paste that code to make life easy. Control C. Yeah, and I will run. And I see that I have my circuit extended with a Hadamard gate. Now I'm going to create a C0 gate. Control Q0, target Q1. Yeah? How do I do that? Circuit. On the circuit, I execute CX. And, of course, the first one is the control. Excuse me for this. QR0 and qubit 1. There are alternative ways to write this. Yeah. More simply, yeah, and I get this one. Yeah. I will make my screen a little bit smaller so that you can see a little bit better. You see? Better, you can see the details better. Not the total view. So this is my bell state in Python. Now I'm going to measure. How am I doing that? Voilà. The syntax for this is also relatively simple. Circuit dot measure method, and I can keep that simple. You see, automatically Qiskit knows that qubit 0 must be collapsed to bit 0 and qubit 1 to bit 1. Yeah? So I don't need to specify that. I get this, and you recognize this probably, yeah, from the previous exercises we did with the quantum composer. This is in Python. Yeah. I repeat, the drawing is for educational purposes. Huh? I don't need to do that every time, but I do that for you so they can see, follow up what is happening. Huh? Of course, when you have a working circuit, you delete all these, if you're putting comment, all these drawing. Huh? This is not necessary anymore. But I did not yet execute something. So now I will do some coding of which I ask you to please accept it. I will explain what happens. If you would say, this is not so intuitive, not so natural, I understand. I even would agree with you. But yeah, it is, of course, set up in the context of a lot of possibilities, a lot of options, a lot of types of problems that need to be solved. And so you have a kind of complex set of syntax possibilities, of which we use just one example. Let me take, first of all, this one, Qiskit. I will explain at once, immediately. Sorry, import. Let me execute, and then I will. So what we do here, import from import IR simulator. What is a simulator? You can already feel what I'm doing. Eh? Simulator. It's a simulator. I'm going to execute on a simulator, not on a real device. But AER, what is that? That is the name of the set of functions that are provided by the simulator. And so accept it. That was invented many years ago by the Qiskit people to use it AER. Yeah. It is still existing. In the meantime, a lot of things have changed, but this is still the name used as in the very start. Then I am also going to visualize in a histogram. So this is a simple one from Qiskit visualization. Oh, I'm typing a lot of errors today. Import plot histogram. What is interesting about this to tell? Visualization. I have multiple ways to visualize my results. That can be a histogram, but I have also a Q-sphere. I have state vectors. I have a lot of visual representations in Qiskit, about 5 to 6. And depending on the problem I want to solve, I can visualize in a certain way. You understand? So we are going to keep things simple today. We would need more time to discover multiple visualizations. In the Qiskit course, there is a chapter on visualizations. So a special thing. We keep it simple. We only use a plot, a histogram. Then. Next one. Result is this is an important one. Now I say execute on the simulator my circuit and calculate the result, meaning the number of combinations for all combinations that occur. Yeah? And I say statistics, this is a self-chosen variable name, of course, is equal to result. And I get the count. I ask for the amount, the number of counts for each combination. Get counts, yeah, that's the one. And this must be results, of course, because I've put results. And then I can say display plot histogram statistics. Yep. And I get my result. 0, 0, and 1, 1. And you see a statistical error, 520. It is not 512, 512. So the default number of shots is 1024. I can increase that number of shots. I can decrease that. I will not do that now. It's another syntax. I need to extend my syntax. I could do that, but I could also say, of course, simply the following, print statistics. Yeah, and then I see the same result, of course, but then 0, 0, and 1, 1. Okay. Yeah, that is. Yeah, I will leave my desk again. That is the world of Python. A very simple example. Okay. Good. Now, next one. I'm taking a look to the agenda. Yeah. Okay. Everything clear? Because then I would like to go to the next exercise. I will make it a bit smaller again so that you can see a more complete overview. So some people might need to put their spectacles, but so I will roll it a bit up again. So I will go over. So this I could delete what I want. I can do as I will delete the drawings here, so that you have everything a little bit closer. Yeah. Of course, needless to say, you can put everything in one cell also. Okay, like that. Yeah. Okay. Then we could easily extend this example to again also the quantum adder, but I will skip that exercise to need a little bit of time. And we will go to the next one. We are going to do now quantum teleportation. I will show you first of all the circuit, and then let's do it. The circuit is as follows. Before I do that, yeah. First of all, some philosophy. I switch off my. Yeah. Is the mic upset? What do we like to do with quantum computing and quantum algorithms? And we are going course, today it's an introduction. But if you take a scientific quantum computation scientist, what are they aiming for? Yeah, you have here a couple of examples. The big O notation, they call it. I don't know if you already studied big O. It's an order of magnitude indicating what is the amount of operations and time you need in function of the number of variables. For instance, if I say I have to check if an integer even or odd, yeah, it's a constant time. If I need to do a binary research, in a sorted list is of the order of magnitude logarithm n. Multiply 2n digits, it's quadratic time, and so on. If I have the brute force traveling salesman problem, you might know that. Suppose this afternoon I say it's nice weather, take your bike and visit 5 friends. Yes. Yeah, you can easily find the ideal, let's say, routing. But if I would say you have 20 friends you need to visit with your bike, what is the best trajectory navigation for one friend? Well, there are 120, there are 20 factorial possibilities. It's a huge problem, combinatorial problem, that is. And so you see a factorial time and factorial or exponential time, integer factorization. This is the red zone. This is really not efficient. What we try to do with quantum algorithms is move from the red zone to the green zone. And sometimes that gets possible. With the algorithm of Shor, for instance, we move from the red zone to the green zone. Yeah. And that is the aim. That is what quantum computation scientists try to do when they come up with a new algorithm. They try to prove how, yeah, we have a quadratic speed up, we have an exponential speed up, that's the ideal world, but it not always happens. Or we are not able to find a quadratic speed up, or is any speed up. Yeah. So our research is not really used. So that's interesting. By the way, there is also, I don't know if did you also study complexity theory, NP hard, polynomial types of problems, non-deterministic polynomial, BQP. There we also have a complete theory, and in which we say we try to solve problems with quantum computers that are NP hard, and that sometimes succeed. I will not go deeper here now, but that's also a complete complexity theory where quantum computing fits in. We'll not do that now. It would take us too much time. These slides, I mean, just one small thing because I like to talk about it. Sorry for that. So you have the set of complexity, the complexity theory. We have the polynomial problems you can easily solve with quantum classical computers. Then you have the non-polynomial deterministic, meaning you can verify that the solution is right or not right in a polynomial amount of time, but not find the solution itself. So verification only polynomial amount of time. And then you have a special category NP complete, meaning that you can reduce your NP problem to an NP complete problem, set of typical representative NP hard problems. And then the NP problems, excuse me, and the NP hard are really difficult to solve. They can even be non-decisional problems. And there is a kind of big contest in computer science, in which they say if you can prove really that P and NP are different, you can make €1 million. And you can, that is still an open contest. That if you find a proof, we can earn €1 million. Yes, I will skip that one. And I come down to an overview of famous quantum algorithms. These are algorithms of which you find a lot in books on quantum computing. You take a look in quantum computing books, you will find all of these described in very detail, with proofs, not always easy to understand. Some of the most famous ones are probably Shor and Gruber. a rule for search in an unstructured list, and short for factoring integers or solving a discrete logarithm problem, but this comes down to period finding. Yeah. So one of the most famous ones. By the way, Peter Shor is born in '59 and still, I don't know if he's still teaching, but he's connected to the MIT, Massachusetts Institute for Technology, so he's still so it's a relatively young discipline. Also, Lou Gruber, still, yeah, I don't know if he's still teaching, but still working, certainly. Yeah. I will not. Yeah, you can imagine that if you would like to explain the algorithm of Shor or Groove, I would need quite some time. It's not so easy. Certainly not to explain how it is proved that it is working. I was once participating to the Qiskit Global Summer School. The Qiskit Global Summer School is organized in July, and it is talking about Qiskit, and there was a proof for the algorithm of Groove. It was done in total in 6 hours. Day 1, 3 hours, day 2, 3 hours, full of mathematical concepts. Interesting, but also it took me also 2 additional days to understand it completely. So it was really, they used a lot of thinking, that you say, well, fantastic, how did that gentleman was able to find that. What we are going to do here is the other ones, teleportation, and then my ambition was to show you the Bernstein-Vazirani algorithm with a small proof, an indication of a proof, not a full mathematical proof, but an indication of how you can understand it. Okay, let's first start with the teleportation. What is a teleportation algorithm? First of all, you need to know that in quantum there is no cloning possible. You cannot say I have a quantum state, and I'm going to copy that quantum state to another state, like you do with classical bits. There's no cloning theory. But of course, we would like to transfer the state of a qubit from a state of one qubit to another. And there the quantum teleportation algorithm can help. We are going to do this now without proving the mathematics behind it, because you can prove it. You can prove it. It's not so difficult to prove, but it would take us a half an hour. So I will show you the circuit, and then I invite you to program it in Qiskit immediately. Yeah. So you have now the foundational layer. You know how to write a CLOT gate. You know how to write a Hadamard gate. You can add barrier. I will show you how you can add a barrier, and the X gate. Okay. So what is? Oh yeah, there is only one new gate. So and I go back again to my yeah. And I will. Excuse me. I made a mistake. I should show you first of all. This is the teleportation algorithm. So great mindset. I will explain you what is happening. So it's already a little bit longer, as you can see. It's already a little bit longer, but not extremely. You have a quantum state here, psi. We are going to start with the simple state, the X state, the not. That is, I will show you that. So, but it is the state that you want to transfer, not copy, to transfer from Q0 to Q2. The barriers are, as you know, for readability. So what we first do is a Hadamard gate. We have an Ancilla qubit, we call it. Ancilla. It's an assisting qubit. When we talk about quantum computing in a circuit, an Ancilla, you would search that in the dictionary, it's help, assistant. It's an assistant qubit to make things happen. So the Q1 is an assistant qubit, and we transfer the state of Q0 to Q2 by doing these steps. Hadamard, C0, C0, Hadamard. That's the inverse bell state. And then we do a C0, and this is a conditional Z gate. A conditional, not yet discovered, a conditional Z gate, CZ, you could say, between the Q0 and the Q1. That's a new gate that we did not yet discuss. Yeah. But I will show you in the code as well. So let us do this. We have, yeah, I think we can succeed doing this in a reasonable amount of time. Yeah. So we could take our exercise we made and adapt it to this one. And I will do that perhaps together with you. So first of all, I will take it like that so that I don't lose my view on the screen. I will go to my quantum lab. And I will go over it. First of all, how do I need to adapt it? And I will. 2 qubits is not enough. I need 3 qubits. And I have enough with 1 classical bit. So I will adapt there quantum register to 3 and classical to 1. And so on. Because I only have 3 qubits and only 1. Then my circuit is okay. The first thing, what I'm going to transfer, as I said, I am not going to transfer the psi here because it is already a complex state. I'm going to transfer the simple state x, the 1, x. That's a simple state, I know, but it just, that's why that was already the first start. So I want, this is the state I want to transfer. And I want to first need to execute it as well. I need to execute it. Otherwise. So, now. I will make a drawing because it's only to give you more confidence. That is what I want to transfer. So I have initialized my circuit. That is a state of which I want to measure it later on here. I know it's simple. I could simply put here an X as well. I know very well. But this is about how I can transfer. And now I'm going to apply these gates. Yeah. You see? Hadamard, and then barrier, and then transfer. So I will stay now on my chair and I will do it step by step. So the first thing I need to do is the Hadamard gate, but on qubit Q1. Then I need a CL gate from between Q1 and Q2. By the way, I will will give you the notebooks. So probably to say just watching. I need to do a signal between you. I will do the various stuff. Okay. Now, I do the signal gate between Q0 and Q1. Then I do the Haramat gate. Zero, and then stop for a couple of seconds. And wow. To make sure I'm still working as it must.
It's okay. Hello.
You see, here I am. I am here, huh? In my teleportation. I am here. Now, next step, last steps I need to do. I need to create a seed of between Q1 and Q2 and a CZK. You will see that, and then a measurement. Yeah? And then I'm going to execute it. And I hope that I will measure a one status in Q2. Yeah? That's my goal. Yeah? What is the next one? This is the code here. The measurement is different. I'm just measuring my Q2, my Q, my CR1. See, circuit is complete. I only have one measurement. Only my qubit Q0, Q2, excuse me, is measured to my qubit C1. For the rest, it's identical, same copy. I was just doing copying work here, but with the syntax. Okay, now I'm ready to execute.
Did everybody manage to get the circuit already?
Excuse me?
but you see not controls over one given to the two.
Okay, I'm going to execute it. What do you see? What do you see? You see, the only result is one. All possibilities, one. So each one is a result. So I teleported my state one target circle. And you could do then other things. I will. The question was, but I want to try. I'm not going to do the teleportation of the following, but you need to help me perhaps there, but I will do it. I will take the risk. I'm going to do the following. I'm going to teleport the following state. The square root of 7 plus the square root of 3. What is that? If you take this coefficient and this coefficient and you square it, you get 1. That is necessary because the qubits are normalized, because the sum of the probabilities of the coefficients in a qubit must be 1. Why? Because the square of, I did not explain it at the start, unfortunately I forgot to tell it. The square of the coefficient of the qubit is an indication of the probability that you will measure that state at the end. And the only thing is do I have the square root in NumPy? I think, I'm not sure, please correct me if I don't. I think it is a.
Yeah, there's NumPy squared.
Yeah. I'm taking a risk now because I need to do too much improvising. Let me anyhow do I make an array. And then something that's Let me explain. It's okay. So what I'm doing here, and I will explain what I'm going to do. Instead of transferring my X, I'm going to transfer a state initialized as a vector. Please accept the syntax now. We don't have enough time to explain state vectors because every qubit state can be expressed as a state vector, two-dimensional state vector. And you see that the coefficients, and I take the squares and I sum them up, I have a total probability of 1. Yeah? And I can use the syntax initialize in qubit Q0. I initialize qubit Q0 with that state. Now I'm going to re-execute a complete circuit without modifying anything. I've just a new initialize, I've just a new value here, the psi, and I'm going to do identically the same. And I'm wondering, I hope it is transferred correctly. That's my I know what happened at the end. Now it's better. You see? I'm doing nothing now, just what do you see in my result? I see indeed that I have transferred 0.7 and 0.3 approximately. I know. But I have respected my coefficients. I've transferred my coefficients to that. So because when I measure, I see indeed. So, of course, in reality, if I teleport it, I will not measure that because then I lose my state. But I can teleport the state from view 0 to view 2. I do the measurement to show you the result, but in reality, I would not do that because I lose my state, of course, by measuring. But I have to show I can do the teleportation. Okay, now a question for the organizing team. How much time do we still have? Can I still?
Yeah, almost a bit more than half an hour.
So we still have about
Half an hour. We can still use half an hour. Yes, let me take a look. I can do the Bernstein-Vazirani algorithm, or I leave it up to you. Do I tell it a bit more about QML, quantum machine learning? Do I do the Bernstein-Vazirani algorithm?
I think machine learning is quite interesting.
or we can take a small poll. Okay, so just very quickly, either we do another algorithm, the Bernstein-Vazirani algorithm in Qiskit, or Eric can also tell us a bit more about quantum machine learning. So I don't know which material you would like to see. So maybe the ones that want to see the algorithm implemented in Qiskit or explained can raise their hands.
Do it yourself. Much more do it like this one.
Yes, a bit like this one, implement an algorithm yourself. So we have 1, 2, 3, 4 hands, I guess. Yeah. And then who wants to know a bit about quantum machine?
It's more demo, and that's more demo explanation.
Okay, so then we will do the demo of the quantum machine learning, and also you probably already downloaded the notebook, so I think you can try the other algorithm at home. Then we will do the quantum machine learning.
And also you find some documentation about the Bernstein-Vazirani as well. It's similar to teleportation as far as complexity is concerned. And the proof is easy. Quantum machine learning is requires first of all, let's say, quantum introduction, and then we can do the Um, Okay, what is machine learning? First of all, why do I like to tell about this? First of all, I am one of the co-leaders of the quantum machine learning community of interest in IBM. And that does not mean I know everything. But interesting is I can lead meetings, I can set up meetups, I give a lot of presentations and demos about it, and I see a lot of things passing around. And so I see a lot of things happening. I don't know everything because there are really people who are much stronger than I in this domain. But it's an interesting domain. Why? Because it allows you to do already useful things with quantum computing even before we have the perfect machines. Let me explain you and convince you that this is an interesting domain. First of all, perhaps needless to tell you, where are we talking about? First of all, artificial intelligence, I don't need to explain you. The only nice thing to see on this picture is the latest evolution foundation models. And if we focus on it's about large language models, it's about transformers, we all know about ChatGPT. When I talk about quantum machine learning, where do you need to see that in this picture? Here, machine learning and deep learning. So it already existed before these foundational models became so popular. On the other hand, we see, of course, integration of usage between both, but I will not discuss that today. We built a nice demo where we integrate both, but I will focus now essentially on machine learning and the deep learning aspects. And perhaps it's good that I show you this. Yeah. First of all, this is also a slide that is probably too easy for you, but why do I use it? To tell you that with quantum machine learning, we see that research is done in all the areas that are applied or done in classical machine learning. This is some examples of classical machine learning. Unsupervised clustering, dimensionality reduction, like PCA, principal component analysis, and things like that. You have supervised learning, the most easy flavor, I call it, and with classification and regression and associated things. And we see that quantum computation scientists are working in all these areas. So people are doing clustering with quantum computing, are doing regression, are doing classification. So we see that it's also applicable to the world of quantum. That's interesting to know already. And then an interesting slide. I always like to tell that because, by the way, it was inspired by a couple of people that you should know if you are interested in QML, quantum machine learning. It's Maria Schultz and Francesco Petruccioni. They have written, authored a very interesting book on quantum machine learning, in which they bring together not only their, let's say, their concepts, but also research results of a lot of people. So we could call it a kind of assembly of research in their area. They use this table, and you will find it in a lot of papers around quantum machine learning because it's so interesting. So you have two dimensions. On one hand, what is the processing device that can be classical for quantum? And on the other hand, what are the types of data? And of course, CC, you all know, that is what we are doing in the traditional machine learning. You have classical data, you have a classical processor, and you try to predict, you try to do regression, classification, classification. But then we have also QC, meaning you have quantum data about quantum mechanical processes, which you are going to process with classical computers. And these softwares exist. If you go to Unicore, not far from here, I think, they use, for instance, a couple of software packages like BAS, like Quantum Espresso. They are really softwares that are simulating quantum mechanical processes, quantum chemistry with classical software. So that is also another. Then you have CQH, the green area. That is what we do in quantum machine learning. It's about, you have the processing is on a quantum computer, but your data are classical. Data what we always use. Traditional data. Data about pixels in a picture, data about you collect what we do every day. That is what QML is focusing on. A derivative, and of course, if you have done this, it is not so difficult anymore. It's QQ, quantum data, quantum processing. But most of the efforts in quantum machine learning are in the green quadrant. And there is a lot of, as I said already, exploration and research going on. Of course, when you see CQ, there is a difference between both, and that is the big challenge. How do you go from your classical data representation to your quantum representation? That's the big challenge that we have. How do you, what we call encode your traditional problem on a quantum computer? And I come back on that with a couple of impressions. That is the challenge. And this is expressed in this small picture. It's a very strong simplification. On the left-hand side, you see what we are doing in always are doing in the classical world. You take data, you train a model, and then you use new data to predict, to classify, and this is a very simplistic situation. Here we have kept the same simplicity, but the only difficulty is the red. We have, first of all, the encoding and the readout. So we have that intermediate situation in a quantum circuit, in a quantum representation. And before getting there, we need to do a smart data encoding and afterwards a smart readout. The readout, that's relatively doable, but the encoding is not easy. So how do I represent you could say, of course, I keep it simple. A bit becomes a qubit. That's the most simple translation. But then you cannot make so much advantage with quantum computing. So the data encoding is important so that you can make an advantage. And before doing that, I have also an interesting slide about the evolution in quantum machine learning. 10 years ago, we saw a lot of people, scientists focusing on quantum machine learning, and they assumed we have perfect quantum computers. So they have theoretical solutions. They proved in theory this solution will work well, but of course it was still tested out on a quantum device. There were not yet existing devices. It was theoretical. We have things like we will have an exponential speed up, a quadratic speed up, and things like that. First wave. But then we come to the second wave about also some more than 5 years now, where we see scientists focusing on what are the available devices today, what can they already do, what is working, what is not working, and in a smart way combine classical and quantum computing. And that is a second wave, working on the near-term approaches, devices, near-time devices, and much more heuristical, empirical, not necessarily a theoretical proof that just do it and try it out. Yeah? And with techniques try to improve the performance. And combine in a hybrid approach, classical and quantum. That's a very pragmatic approach. In the meantime, we see a third wave. And what is the difference? Here we still think classically, we could say. We think in a classical way, the algorithms we're using already exist, or more or less. We modify them a little bit. But in the new way approach, there are people who are thinking in a, I would call it, more quantum-oriented way. What can they start from the quantum phenomenon? And how can I use these to develop new algorithms? So, okay, that is a new way. To be honest, I am today much more focusing on the first and the third and second wave. And the first wave, to say that I will not dive too deep here. The first wave is really about the acceptance we have full tolerant perfect machines. Yeah? And what I do is what we always have been doing in our classical approach. We now just try it out, or we propose a quantum alternative approach. For instance, quantum glass, basic linear algebra subroutines. Basic linear algebra subroutines. So the linear algebra that is used in machine learning is translated to the world of quantum. And for instance, HHL, you might have Hasse-Dimmer, Ferros, and Lloyd, I think, method of linear equations to solve the problem. Support vector machines, I will not read them now, but a lot of things that already exist in the classical world are repeated, but with a quantum algorithm replacing the original traditional classical algorithm. You have also a wave of methods that is based on Google search and probabilistic methods also exist. Bayesian nets, Boltzmann machines, you might have heard about them in your courses. So they have also a quantum alternative. The only thing is they assume perfect quantum computers that we don't have yet. So the theory exists, but we will still need to wait until we have perfect systems before they will be executable. Next one. This is an overview of multiple algorithms. I will perhaps skip this slide and go to the near-term ones. So these are the quantum machine learning algorithms that don't need perfect quantum computers. So they already run on, let's say, the NISQ systems. And we see three big categories. And you see also one of the breakthrough papers for each of them. But there are more, there are much more. The first one is support vector machines. Do you know about support vector machines? Classification. And so you have a way to classify, and there is a quantum alternative. And I come back on that in the next slide. So it is about classification, also used in regression. What we see there is that this traditional algorithm can be replaced by a quantum algorithm that is doing let's say, a job that is equivalent as good as to classical machine learning. A second wave is quantum neural networks, and I will also come back on that, in which we see that the name suggests it's a quantum alternative to neural networks. And neural networks in deep learning have multiple layers. The result of one neuron, multiple neurons, is used in the next one. This is equivalent. You see in a typical circuit that you will have a parameter. That parameter theta is initialized and is then optimized so that the result converges to a certain result. So you combine it with a classical optimizer. A classical optimizer, a parameterized quantum circuit, they call that a variational quantum circuit that is put in an iteration, and you converge to a certain value. What do you converge? You have a loss function. And you might know that in machine learning you have the loss function that is calculating the difference between what you predict and what you should predict. And this loss function is optimized with you start with the parameter and you try to modify the parameter step by step so that you get to a loss function that is minimal of 0. Yeah. And then you end up with the optimal the quantum circuit, and this quantum circuit can be used to predict new values. So you do an incremental improvement of your quantum circuit based on a parameter. That's the way, and I will show you a small overview of that notebook in a couple of minutes. And a final approach that is really making a lot of getting good result, getting popularity is GANs. GAN stands for Generative Adversarial Network. To make a long story short, it's about generating data for synthetic data. You know how important it is to have the right data in machine learning. You have, of course, your real data. You need to anonymize it. You must make sure that there is a right balance, that there is a right scaling in that data. You might know that in machine learning. And with GANs, we can create synthetic data, artificial data for your machine learning. With quantum GANs, you can do that. It is based on what we call a discriminator to find what is good and not good. And I will not explain everything, but the goal is to generate data for other machine learning algorithms, can be quantum or classical. And so it can be combined with classical and with quantum machine learning. Yeah, that are the three areas where we see concrete usage of both. And then something more about encoding data, and then I still take 5 minutes and I'll go to an example. Encoding data, so I repeat, so how are you going to make the translation from your classical world to a qubit representation? What you see there is some approaches. You see some examples. The first one is the simplest one. Each bit becomes a qubit. But you lose the power a little bit of quantum. It's not always most efficient, and not always creating an advantage. The second one is a situation in which you say, you see the qubit state as the sum of basic states, all zeros, 0, 1, and you're going to use the amplitudes. As we did in the previous exercise, 0, 7, 0, 3, you're going to use these types of values to represent your data. Which is a bit different about it. And the third one is difficult to explain because we did not yet see the relationship between a Borg sphere and it's another approach based on the rotation angles on the Borg sphere. More difficult, more complex. Another one is arbitrary encoding. In which you say I encode with a special quantum operation. Of course, this requires more, let's say, exploration, deep research to do that. Not so easy. It can be any, let's say, gate or combination of gates to represent the problem. It depends on the problem you want to represent, but it is it can be multiple things. It would need more time to explain that, but I can explain you the impact of that collection. So, you see here 3 examples of data encoding. Then I repeat, the data encoding is translating your traditional data to quantum representation. In the first situation, we have used, and just forget some of the details here, but the compression is important. We have used a simple representation with no entanglement. only Hadamard gates are used. Here we have used Hadamard and CNOT, superposition entanglement. And here we have used even more complex combinations of Hadamard and entanglement. And you see the impact. Here it is much more granular, much more fine, much more correct, the classification. Because the orange and the blue are different zones of common classification. And you see, this is much more contained, it's much more coarse, I would say, much more less refined. The classification here is much more correct. Because the zones are much smaller. What we mean by this is that when using more sophisticated quantum phenomena like superposition and entanglement, your results become more accurate in the classification. This is a research done by some people. So the encoding is important. Having good results. Okay. And this is an example of a closed support vector machine. Also here I have extracted this from a large set of. Then you have this one, the blue and the red, and you have to classify them. And you have 2 dimensions. It's difficult. You cannot draw a straight line in the 2-dimensional space. In a support vector machine, you might know, we are going to transfer the data to a higher dimension. And there we are going to classify. Things like you see, we're going to the 3rd dimension, and then we can find a separating hyperplane between the blue and the red. Because that is what support vector machines is about. It's about putting your data in a higher dimension and hope that find there a separating hyperplane from 2 to 3, from 3 to 4, and so on dimensions. To make a long story short, this, let's say, move to a higher dimension, we call that the kernel trick. And this can be done with quantum computer. So the quantum computer can be the kernel of your support vector machine. And this seems to be very efficient. Yeah? And where you can make a difference with quantum computing. The kernel is more efficient than classical computing. Okay. This is, as I already illustrated, a quantum neural network. It's about combining parameterized circuit and other circuits, and you try to optimize the parameters via iterations. It's a general representation. Okay. Okay, before I go to the demo, how far are we with quantum machine learning? Some people ask then, do we already have quantum advantage with quantum machine learning? It depends how you define quantum advantage. We as IBM, we say quantum advantage means you can solve a real problem that makes sense for science, for business, for society in general. Faster, more accurate, with less energy consumption. To be relevant, faster, more accurate. We are not so far. We can solve problems faster, but they are often not really creating added value. Or we can solve problems that make sense, but the speed is not so much different. The reason is that we have still noisy systems, but that will improve. So quantum machine learning is certainly a promising area of science with a lot of focus. Where some people say it will probably be the first area with a breakthrough in quantum machine, in quantum computing. I know it was very quick, this video is very short, but I will show you now one notebook, an example of the quantum neural network. Excuse me that I sometimes need to skip there some things, but I will tell you the most important things. So, and I need to start, I have my own local environment, but I need to start that. It will take only a couple of minutes. Let me take, Oh.
It's fine. It's okay, you can just go to the demonstration and we can put off the recording. If there's a problem.
Are you still in the
This is my local installation, and I will now share my screen again. Yeah, just a second. Yeah. Here it is. Share screen. Entire screen. Yeah. Okay, should be okay. Yeah. Good. Yeah. My apologies for the interruption. I go to so mijn excuses en ik ga do this one. Yeah, and I will not execute the notebook. I will only show the, yeah, should come, yeah.
how?
So this notebook, and I can share it with you, no problem at all. So what we are going to do here is, we use here, you might know the Iris data set from the world of machine learning. You know that? So you have, it's a kind of, you know that scikit-learn, you have a lot of data sets available for learning purposes, and the Iris data set is one of them. The Iris data set is very simple. It's you have 4 features for the beta length, the width, sepal length, 4 of the leaves. And they can determine then the type of iris flower. There are 3 types of iris flowers, and based on the characteristics of the plant, you can predict what type of flower it is. It's a simple data set. It's very known outside the quantum already exists for many years. The node iris data set you can easily use. It is also used in a lot of classical examples. People are learning machine learning. They use also the iris flower data. And yeah. So first of all, as you can see, the structure of the data set, it's you have here everything is written. You have sepal and petal are the kinds of leaves that the plant has, and you have a length and a width in centimeters. 4 columns, and the 5th column is really what is the type of, here there are 3 types of iris flower, setosa, versicolor, and virginica. Okay, that's the data. So if it is also outside of quantum. Okay, and then what we see here, yeah, this is traditional thing. I will make it larger.
Control plus. This is traditional, nothing special. What we typically do in machine learning is scaling the data. And we have seen that the length and the width are different, let's say, distributions, and also the minimum and the maximum value is completely different. We want to put them all on an equal level by scaling them between 0 and 1, so that you can use them really. Otherwise,
So normalizing the data in some sense.
yeah, normalizing the data. Normalizing the data, because that's the right word. Yeah, that is of course traditional stuff. Yeah, this is also traditional stuff, just to show you the three types of flowers and how their characteristic is behaving. Sepal length, and then it is mapped against the other parameters. Just to show you, we have three types of flowers which are really different in characteristics. That's the only thing we do here. Still traditional, nothing special. So we train a classical machine learning model, and we are using for that, still here, just a second. Yeah, this is the one. We have here, we are using SVM from the SVC class, support vector class, and we have split up the data in training data, training labels. The labels are the types of flowers. The training features are the 4 columns with the leaves. And then we are going to make a model. Yeah, and I will remember again. And we see that with the classical algorithm that you find in scikit-learn, nothing to do with quantum, we see that we have here a score that is evaluating the model, the classical model. You see relatively good model. So that means that when I give you 4 characteristics of a flower, the model will very well predict what type of flower it is out of 3. So, and then we see with an equivalent exercise with quantum computing. So we are going to quantum machine learning, and I have put some explanations here. Yeah. Okay, that's the first step. Yeah. I could spend here a lot of time, of course, but I will keep it very short. First of all, you see that we have 4 qubits in this circle. So we are, each feature of the flower is represented as 1 qubit. And we are going to visualize what we call the feature map. So that is the encoding, meaning that we are going to create a lot of variability in input. And you see that we do that with 0 gates, do that with phase gates or rotations around the axis. And we see also some other. So this is the initialization circuit. So you can see that it is. It requires a little bit more time to explain that, but you understand now a little bit the basic concepts. Then we are going to make use of an ansatz, as we call it, also 4 qubits, meaning we see here the parameters. That is really, you see in total 60 parameters normally, also 4 qubits. And this is the circuit that is going to be trained, that is going to be optimized so that we find the optimal parameters. And when we have the optimal parameters, we can predict new flowers. This is the, let's say, the part with the parameters that must be optimized to the quantum neural network. Yeah. Okay. And the optimizer that we use for iterations is the probability optimizer. There is also a classical optimizer. There are multiple others. There are 3, 4, 5, even more optimizers. You use other iterations. And that are the parameters you could play with. You could use another type of optimizer, another number of iterations, and so on. But okay, that is what the data scientists need to do. Experiment with the models, experiment with the number of iterations. And then I'm going to plot and to measure. Yeah, then I'm going to do the training and to execute, sorry, and I'm going to execute the model I have trained and see how it evolves. And you see I have a loss function, an objective function that is conversion to 0. Yeah. I calculate the score and I see that, yeah, my result is not that, but the classical result was still better. Yeah, okay. But I have a second execution, I think, in which I have a better result. Because I am going to use a little bit to reduce the number of features with principal component analysis. And I go a little bit further and I come to a little bit better result. So to make the long story short, of course, this is just giving you an impression. We already have quite some libraries that allow for quantum use cases that are compared with classical results. Sometimes the results are better, sometimes they are not equivalent. But yeah, so that is what I wanted to say. And so they are available. So it's a combined existing things with not complete new inside. I hope it gave you a good impression. Yeah.
Okay, are there any questions for me about machine learning or about some other part? Maybe I can start with a question. So now a lot of the hype in machine learning is around these large language models, of course. And one characteristic is that they are large. They are very, very large models. And it seems, at least in the near future, that with the quantum machine learning, we will go more towards a smaller network. So can you maybe comment on which problems would be maybe in the near future or foreseeable future suited for quantum machine learning, rather than things that are maybe more suited for classical?
So I understand the question. First of all, we need the space of generative AI with very large models. And you look at that this global classical computing has an advantage. Because, as you say, indeed, the number of parameters in such a large language model, we talk about billions of parameters sometimes. That is not yet possible with quantum computing today. We don't have enough useful tools to do that. On the other hand, indeed, there are some problems where we can say quantum computing can be the right alternative. And that is in classification, but we can go to the classical situation, the typical situations of classification, of regression, also clustering. And let's say that the traditional machine learning progress, there I see the first advantage for me. Not the large language models. I think that is this moment on short term really doable.
Okay, thank you. Other questions? Okay, if no, then for Beth, you have a question?
And over the, let me say, BSc quantum computer, or do you think that the Spanish government will invest in IBM system?
And the government, that's a good question. Is the government going to invest in, that's a very good question, that's of course, yeah, what do I see in Europe, first of all. We talk about, allow me to talk about Europe and then about Belgium and about Flanders. We talk about the three regions. First of all, in Europe, I see a lot of not much more attention for quantum computing, but a little bit to what we don't like to see is that they also thought we are going to build our own quantum computing. While there is already quite some knowledge and skills in the world available,
Of course, it might come from the US, but we also have it in Europe. I think it's not the right choice by the European Union. We should say we are going to build our own quantum computer. I would reuse more what other suppliers already have been doing. So, but okay, my opinion. Or at least leverage it. Yeah. Yeah. By the way, now we got during the break that question. A good example is IMEC and IBM are very close in contact about the classical and the quantum world. By the way. So the second thing is Belgium, but I would, yeah. Then I would first like to turn to Flanders. Flanders, we have a lot of contacts already in the area of quantum computing. There is attention by the government. I can even say that our minister president visited the Fraunhofer installation. So they are looking at it. But the problem is a little bit who is going to drive, let's say, the initiative. Who is going to take up, who is going to start a quantum innovation center? You could say is that the university, National Computer Center, is that PIB, France Institute for Biotechnology. So I see a lot of attention to others. Let's see to my perception, might be wrong. So what the government is searching for is who is now the right instance to start up the quantum initiative. That's the current situation. But for us, it would make sense, of course, because in a lot of regions you see that there is investment in quantum, perhaps after the elections. There might be budget, but we think it's time to invest in. If you see Copenhagen. It's the region where the NATO has started a quantum center, quantum computing center, and you see a lot of universities and spin-offs coming into systems that are investing in quantum.
Do you think it was utilized in the US or in Europe? Because I heard that the European Commission is a bit, a lot of companies are moving away from Europe to the US because there's a lot more potential there and investment opportunities. But do you think there's still as much potential here as in the US?
I think there is still potential. Yeah, in my opinion, my feeling is that there is certainly most everything will move away from the US in my opinion in that space. I see also European initiatives, as mentioned, that in Basque Country, Germany, Denmark, interest. I don't think that's actually, I think there is still possibilities, talented people to stay in Europe around one, certainly.
IBM still have like fusion projects in Europe as well.
We have our main center for quantum research is in Zurich. We also have in Germany, essentially in Zurich. Other things I would like to add, we are talking about geopolitical things. It seems that in China, the investment in quantum is 3 times as much as in the US. That is why quantum safety is so important for humanity.
I think we have time for one last question.
Well, I see that the thing that you have on the aspiration and the expectation. I show anyone else who know how it
If you have an app, I would say try to execute it again. Normally it should be okay, but I will take also a look to my results if I have one. It should be okay normally, but I was one step too far. Yeah, mine failed as well, so I don't know why. Something went wrong with the transpilation. Yeah. Explore it. Something was fundamentally not working with the transpilation. It might be a temporary problem. That's the advantage of a free environment. Sometimes it's working well.
But in any case, thanks a lot, Erik Michiels, for
Yeah, thank you very much. Thank you very much. And thank you for your cooperation, attention, and interest. And I hope it was useful and you can do something unique and get interested to take it next step. Yeah.
and so for the students.